Okay, second video of the chapter. Let's talk about this guy. Well, not really so much about him, but what he said, okay? So we've got to investigate Hess's law in qualifying the enthalpy change, so whether it's negative or positive, for a stepped reaction using standard enthalpy change data and bond energy data, for example, and here's a reaction. Okay, what we're going to do is use this guy's idea, okay? So it's an application of the law of conservation of energy, and we're applying it to chemical and physical changes, but mainly chemical, okay? It states that the energy change between two chemical or physical states is constant despite the path taken. Okay, we'll go into more depth about what that means, but we're saying that where you start and where you end in your chemical or physical reaction is a certain energy change. Now you can go from the start to end in one step, or you can go to the start to end in 2 steps, or you can go start to end in 3 different steps, or you can go start to end in infinitely many steps. And the difference between your start and end is always the same. Okay? So this is powerful because we can use this to quantify energy changes when you don't know the information from start to end, but you know all the steps in between, okay? And we can treat it like a big puzzle. Okay, so for example, we've got a combustion reaction of carbon with oxygen, well, combustion, it's with oxygen, to produce carbon dioxide. And we've got an energy diagram for this here. We've got carbon and oxygen on the left, so carbon solid and oxygen, and we're making carbon dioxide on the right. And it's lower energy, it's more stable, and we've got a negative enthalpy, which is negative 393.5 kilojoules per mole, okay? So we can take another pathway in this reaction too, okay? So we've still got the same start, and we've still got the same end, but say you didn't know that enthalpy value, what you could do is, if you can have some interim kind of path here, and what we've got in as our interim kind of path, our in-between step, is this one here, where we've got carbon gas and 2 oxygen gas, or we've got completely separated atoms, okay? And if we know that the energy that it takes to completely separate the atoms from here is positive 1210 kilojoules per mole. And then if we know, once you have carbon gas and 2 oxygen gas and you recombine them to form carbon dioxide, you get releasing 1604 kilojoules per mole. What you can do is, from these 2 enthalpy values given, you can add them together and find out the enthalpy without actually measuring it. Okay, so down here I've got the energy required to break the bonds, which is positive 1210, and then plus the energy the energy that is gained, so negative 1604 to put it back into carbon dioxide, add them together, and what do you get? The negative 394 kilojoules per mole. So you don't actually need to do this direct path reaction to find out the enthalpy. You can go via a different path altogether, as long as you start at the same place and end at the same place. Okay, we started at the same place and we ended at the same place, but we took another step and we measured the enthalpy for that, and we could work out the enthalpy for the start to beginning. Okay, so we can choose yet another pathway. We can put many pathways in here. So here I'm just trying to show you, so you had 2 steps in between them. You've got, in purple, you've got this step where you got a lower product and then a higher product, and then you're coming back down. Whatever pathway you take, you adding all the enthalpies, you're still going to get the same enthalpy from beginning to end, negative 394, no matter how many steps. And you can do it an infinite amount of steps. Ridiculous, but trying to demonstrate it doesn't matter as long as you start and end at the same place, and you know all the enthalpies but one, you can work them all out. Okay, so here I'm trying to use an analogy, okay, and it's a bit different because I've got a 2-dimensional analogy here, okay? So the different distance between Wollongong and Sydney is always constant. Let's forget about continental drift. Well, they're on the same plate, but they're always constant, okay? So the trouble is that unless you've got a jetpack and really good navigation skills, your path from Wollongong to Sydney is not in that shortest line possible, okay? But you can calculate that shortest line possible by taking a different path, okay? So here I'm saying in yellow, you could go to Picton, and then you can go from Picton to Sydney, and by knowing the distance and the angle for both of them, you can still work out the distance between Wollongong and Sydney, okay? So you're adding a different pathway, but because in this analogy you know the distance and the angle, you can still work it out. And here in the pink, you can go out to Yerrimbul, and then up to Picton, and then out to some place in the middle of a forest here, and then up to Western Sydney there and across. And as long as you know the distance is the angle that you travel in, you can still work out the direct distance between Wollongong and Sydney there. Okay? So that one's a bit more complex because distance and angle. So in one dimension, like we've got with energy, yeah, it's either greater or lesser energy, it's a bit easier. So I put this analogy in. I've got Janaea, Sarah and Casey all lined up just along a line, one dimension, okay? We know that Casey is 12 meters to the right of Janaea. We know that there's 12 meters there. Okay, we know that Sarah is 4 meters to the left of Casey. What is the distance between Sarah and Janaea? This is our question mark, okay? Now you can see, you probably dealt with problems like this in maths before. That's quite easy. You can not know this and work it out from the other two, okay? So this path here, which is our unknown, we can work out by taking a separate path from here back to here, or positive 12 meters minus 4 meters, okay? So we know it's going to be 8 meters in there. So this is like what Hess's law is saying. You can take another pathway, and as long as you know the numbers of the different pathway, you can work out your unknown. Okay? And there we go. So here, what is the heat of combustion for carbon forming carbon dioxide? This question here. Our enthalpy is what we're asking for. We're given two facts. We're given that this one here, 2 carbons plus oxygen will go to carbon monoxide, which has an enthalpy of this data, and then we can go carbon monoxide plus oxygen goes to carbon dioxide and has that enthalpy, okay? And if you have a look, you can see that we're starting with carbon and oxygen like we are here. Maybe I should change colours. This matches up to here, and we've got carbon monoxide. But then down here in number 2, we've got carbon monoxide too, and we're ending in carbon dioxide here. So we're essentially going from carbon and oxygen, we're going to carbon dioxide. I'm just guessing that it's lower, I don't know. And we've got a different pathway that has some carbon monoxide and oxygen in there, okay? So we're asked that, and we're given this, and we're given that, okay? So I can draw a graph, and you know what? I could probably do a better graph given the enthalpy changes here. But what you can also do is just do it from the formulas, okay? Numerically, it's much easier, okay? If you add these two together, so if you take, what I've just done is added all the left-hand side to the left, and added all the right-hand side on the right here, I just wrote it like that. And then, remember what we do with ionic equations once we've done oxidation and reduction, we can cancel any species that are identical on each side. So here we have 2 carbon monoxides and 2 carbon monoxides. And we have, and that's it. So we get 2 carbons plus 2 oxygens going to 2O2, which is 2 times what we're looking for below. And if we divide it down by the lowest common factor, we get the equation that we're looking for. So what we did to get the equation that we're looking for is we took, I'm going to number this one 1 and 2. We took number 1 and we add it to number 2, and then we divided it all by a half because we had half the stoichiometry. Now, whatever you do to the equations, you do to the enthalpy values to find the right enthalpy. So therefore, the enthalpy is going to equal enthalpy 1 plus enthalpy 2 on 2. And I've worked it out here. It's negative 394 kilojoules per mole. Okay, so when numerically solving Hess's law problems, what you can do is add the given equations in a set combinations to get what the chemical reaction that you're looking for overall. So you can forward or reverse or change the stoichiometry, but you're adding some combination of the given equations in the problem to derive your initial equation, what the question's asking for. And then you follow that same process with the enthalpy values given in the question. Okay. I know that's a lot of words. Let's do an example here. Okay, determine the enthalpy for this reaction using Hess's law. Okay, so we've got potassium hydroxide and hydrogen ions going to potassium ions plus water. Okay, so it's asking us to determine the enthalpy. So I'm going to label that just delta H and put a question mark there. And they've given us, oh, I should have put 1 there. They've given us 2 equations here, okay? They've given us potassium hydroxide going to potassium and hydroxide, and they've given us H plus OH going to water and the 2 enthalpy values there, okay? So what I'm going to do is find some combination that I can put 1 and 2 into to give me that initial one, okay? And what I can notice straight away is, I'll change colors, but on the left-hand side here, I've got potassium hydroxide. Now, in the 2 equations below, number 1 has potassium hydroxide solid on the left. So what I'm going to say is, I want number 1 as it is, okay? And another thing that I notice here is on the right-hand side is I've got water I've got water, and the only place that water is in 1 and 2 is on the right-hand side already, and it's in the stoichiometry of 1. So this is hinting that I might not want to change much, okay? I might not want to divide or multiply my stoichiometries of either, and I might not want to reverse them. What I'm kind of feeling is, what happens if I just add these 2 together, okay? So with these type of problems, what you want to do is muck around a bit and try to get them kind of looking similar, and then just try adding them together and see what you get. If you don't get what you're looking for, you can go back. But here, I've given you a simple one. Okay, so what I'm going to do is just on, I can draw my line here, I'm going to write down all the reactants. I'm going to add these 2 together. 1 plus 2. So 1 plus 2 is going to give me, from the top one I've got potassium hydroxide solid, and from the bottom one I've got a H plus and a hydroxide. Okay, that's all that's on the left of both equations. On the right of both equations, from the top, I've got a potassium ion and a hydroxide ion and a water. Okay? Now let's start cancelling. I'll change back to red. Okay? I have a hydroxide on both sides. Okay? Now have a look. Potassium plus H plus. Look at the top, potassium plus H plus. And sorry, I'm saying potassium hydroxide plus H plus. And here I've got potassium and water, potassium ion and water. That's the same as my right-hand side up the top. So I know that 1 and 2 are giving me what I'm looking for. Okay, so that's a good tick. So therefore, to find the enthalpy, I'll keep the same color, is going to equal the same thing that I did to the equations. Okay, I need to take the enthalpy of 1, because I took equation 1, and I added it to equation 2, so I'm going to add it to enthalpy 2. Okay, now I can put the values in. So I've got negative 56 kilojoules per mole plus negative 55 kilojoules per mole, and that equals negative 111, doesn't it? Kilojoules per mole. Didn't need to get out my calculator there. Okay. So a nice simple one to start off with, where we just had to add them in the correct stoichiometry, and we didn't need to reverse anything. Let's try a different one, and here I've done a graph too. Okay. Oh, look at this one. Carbon and oxygen going to carbon dioxide. Given these two here, I'm just going to do it using this equations, okay? All right. So, there's a couple of ways that I could do this. I'm just going to do it like I did before. Okay, carbon solid is on the left and carbon solid's on the left there. That's good. Carbon dioxide's on the right in what I'm looking for, and carbon dioxide's in the right what I'm looking for here. What I'm going to do is, I'm feeling like they're orientated the right way. I'm just going to add them together and see what I get. Okay, so all on the left-hand side. So I'm going to go 1 plus 2. Okay, I've got 2 carbon plus O2. And plus, from the number 2 equation, I've got 2 carbon monoxides. Oh, help if I put carbon monoxide, wouldn't it? And O2. And I know I'm starting on a new line here. It's annoying me too. What are all the products? Carbon monoxide gas. Oh, I've got 2 of those. And 2 carbon dioxides. Okay, let's cancel anything that out appears on both sides. Okay, so 2 carbon monoxides and 2 carbon monoxides. Okay, and what do I get? 2 carbons plus 2 O2s, because I had the 2 there, giving me 2 CO2. Okay, compare this to the original. Well, it is the original, but it's 2 times it. Okay, so what I'm going to do is then divide it all by 2. Okay, divide it all by 2, and I'm going to get carbon solid plus O2 gas going to carbon dioxide gas. Yep, one more, which is the equation that I'm looking for. Okay, so what we did to find the equation that we're looking for is we took equation 1 and we added it to equation 2, and then we divided the stoichiometry by 2. So that's what I'm going to do to the enthalpy values. So the enthalpy for the whole thing is going to equal the enthalpy for 1 plus the enthalpy for 2 divided by 2, which equals, the enthalpy for 1 was negative 224 kilojoules per mole, and the enthalpy for 2 was negative 564 kilojoules per mole. And I'm going to divide it all by 2. Have I got it? I've got my calculator here, which is good. So, negative 224 minus 564 divided by 2 equals negative 394 kilojoules per mole. And that's reassuring because we've done that problem earlier. Different way. Okay, example 3. What I'm trying to do is up the ante a bit. So we've got nitrogen and oxygen going to nitrogen monoxide. And here in 1 and 2, you can see we've got nitrogen and oxygen going to nitrogen dioxide. And then nitrogen monoxide and oxygen going to nitrogen dioxide. Okay, so looking at the top, I've got nitrogen and oxygen on the left, and number 1, I've got nitrogen and oxygen on the left. So I might just leave number 1 by itself. Okay, now on the right hand side, I've got nitrogen monoxide. Now down the bottom here, I've got nitrogen monoxide on the left hand side, and I want it on the right hand side. So what I might do is negative of 2, or swap it around, okay? So I can do that and remember what it does to the enthalpy value, but that's okay. Okay, so let's swap it around. The negative of 2 is, I've got NO2 gas going to NO gas plus a half of O2 gas. All right, that's a bit better. But if you look at the products on the one up top, it's 2NO, okay? And here I'm just getting 1NO. So what I might do is multiply it by 2. So negative 2 times 2 is 2NO2 going to 2NO plus a half times 2, just the 1 oxygen gas, okay? So now I've got my right product there, which is my 2 NOs. What I might do is try adding them together now, okay? So 1 plus negative 2 times 2, okay? So on the left-hand side, number 1 I wasn't changing, so N2 gas plus 2O2 gas. And I'm adding on, this one here, okay? So what's on the left? Plus 2NO2. Okay, that's the only thing on the left of that one. And going back to number 1, the only thing on the product side was 2NO2. And what's on the product side here? 2NO plus O2. Okay, let's look what cancels and see what we get. There's no other N2. 2O2 and O2. We can get rid of the 1O2 and just leave the 1 on that side. And then 2NO2 will cancel with 2NO2. And what have I got? I've got N2 plus O2 going to 2NO2. Hang on, I've done an error here. I've copied that down wrong, haven't I? I can hear you screaming at me already. That's just 2NO. I was going, why have I got more? Okay. NO, that's better. Whew. Okay. So, I got my right equation now. What I took was, so my enthalpy is going to equal the enthalpy for 1, because remember I didn't do anything for 1. And then what did I do to 2? I reversed it and multiplied it by 2. So negative 2 times the enthalpy of 2. Okay? Enthalpy 1 is positive 66 kilojoules per mole, and negative 2 times negative 57 kilojoules per mole. That's not a good 7. That's a bit better. Put it in my calculator. 66 plus 2 times 57, 180 kilojoules per mole. Did I track my negatives right? Negative 2 times and a negative 57? Yeah, it seems good. All right, hopefully I got that right. I think I kept track of all my negatives. Okay, on to a hard example. Look at this. Same type of thing, much more detail in here, but still, we've got a reaction that we're trying to find the enthalpy of, and we've got 4 that we need to find it from, okay? Self-heating cans can be used to warm drinks such as coffee. Very popular in Japan. When the button on the can is pushed, a seal is broken and it allows water and calcium oxide to mix and react. So calcium oxide mixes with water and calcium hydroxide is produced and it releases heat. Okay, so we know we're aiming for a positive enthalpy here. Heat is left over. The equation for the reaction is calcium oxide solid plus water going to calcium hydroxide. And we've got these 4. I stole this question. It's a really good one from this link here. So thank you to the people of that link. Good questions. This one's a nice hard one. So what we're essentially trying to do is get that first equation here from these other ones, okay? What I might do is I find it easier labeling these 1, 2, 3, and 4, and this 1, 2, 3, and 4, okay? So I'm looking for calcium oxide in the below ones, and the only place calcium oxide is, and it's good, it's solid, is in number 1 there. So what I might do to number 1 is reverse it, okay? So negative 1 is going to give me calcium oxide going to calcium solid plus a half of oxygen gas, okay? Now, have we got water anywhere else? Well, we need water on the left-hand side, and it's only in 2 as the right-hand side. So I'm going to take negative 2 of 2. I'm going to take the reverse of 2. And so go water goes to H2 gas plus a half of O2. Okay, so I've got the left-hand side of my equation. Now let's try for my right-hand side. Okay, so I'm looking for calcium hydroxide aqueous. The only place that is down here on 4, and so it looks like it's all good. I'm just going to take 4 as it is. But you'll notice on the left-hand side, I've got calcium hydroxide solid. So it's just 4 is just a change of state from solid to aqueous. So I'm going to have to cancel out calcium hydroxide solid. Now the other place calcium hydroxide solid is on the right-hand side of 3. So it's on the opposite side there, okay? So I'm not too worried about that. If I add 3 and 4, you can see that the solid calcium hydroxides are going to cancel. Now, keeping 3, looking at the calcium solid, I'm a bit worried about that, but if I look at the negative of 1, I've got calcium solid there on the right, okay? So I'm starting to see a pattern that's all falling into place. What I'm going to do is take the negative of 1 and the negative of 2 and the positive of 3 and the positive of 4, or just 4 as itself and 3 of itself, sorry, I should say, and add them together, okay? Let's see what we get. Going to need to draw small and leave a big space. Okay. So I'm going to put my big arrow in the middle to try and keep it all together. So I'm taking the negative of 1 and I've done it here. So I've got calcium oxide solid. Oh, and that's it. And the negative of 2 had water liquid. Okay. And then 3 has calcium solid and O2 gas and H2 gas, and 4 as it is has calcium hydroxide, oh that's a 2, as a solid, and that's it. Okay, now I'm going to do the product side. So the product of negative 1 is calcium solid and a half of O2, and the product side of negative 2, sorry, the one that I just did here, is hydrogen gas plus a half of oxygen gas, O2 gas, okay? And now 3 as it is has just calcium hydroxide solid. And 4 just as it is just has the calcium hydroxide aqueous. Okay, let's start cancelling. Alright. Okay, calcium solid is gone. Okay, calcium hydroxide solid is also on both sides. Hydrogen can go, H2 and 1H2. And let's look at the water, the oxygens, okay? I've got, on the right-hand side, I've got 2 half moles, so 1 whole mole. So that will cancel that with that 1 whole mole. What have I got left, okay? I've got calcium oxide solid plus water going to calcium hydroxide aqueous, which is what I want, okay? That's the equation that I want. So if I want to find out the enthalpy, I need to do the same thing. I'm going to take, we took negative enthalpy of 1 and the negative of 2, and we just added 3 as it is and 4 as it is, okay? So therefore, what's my value for H1 is negative 635 kilojoules per mole. And I'm going to minus whatever enthalpy 2 is, negative 286. Okay, and then I'm going to add on H3, which is negative 986, and I'm going to add on the fourth one, which is negative 82 kilojoules per mole. I'm going to put all that in my calculator. So negative of negative 635 is just 635, and minus 286 is just plus 286, and then plus minus 986 is minus 986, and plus negative 82 is just minus 82, and I get negative 147 kilojoules per mole for the above reaction. Okay, if you could do a problem like that, you won't get a harder one in an exam. All right, there's some more examples there from the textbook, and if you need some more help, questions from the textbook, and we'll leave it there.